Section 5.6, complex numbers. In this section, we're going to be able to identify a complex number and add, subtract, and multiply those complex numbers. So the first thing we want to talk about in complex numbers is we need to talk about the imaginary numbers. Most of you, everything that we've dealt with so far has always been a real number. And the concept of an imaginary number may be something that you haven't really thought about before. But the imaginary number, there's one imaginary number that we use, and that number is defined as the number whose square root is -1. And it's something that we just can't quite put our finger on it, because by definition of square root, we know that the square root should be, if I take a number times itself, it gives me the result that I'm looking for. But in the case of a -1, what is that number that you can multiply times itself that's going to give you a -1? Because we know to get a negative, we have to have a positive and a negative. Well, then I'm not multiplying a number times itself. But somewhere along the way, there has to be a number that exists that if you multiply it times itself, it would give you the value of -1. So that's where the idea of an imaginary number comes from. It's kind of like some of our other numbers that we can't just quite put a finger on, but we know they have to exist. They have to be there. Okay, so when we talk about the square root of a negative number, what we're really going to do is we're going to separate the square root of the number from the square root of the negative part of the number, if that makes sense. So let me show you with some numbers here. It might make this make a little more sense to you when we talk about our numbers here. So what I'm going to do is, if you look down here at the bottom of my slide here, I have one in particular that I've worked out for you already, this one right here. And if I take you through the process of what I've done here, you'll look and you'll see that I started with the square root of a -4. Okay? By our rules of exponents and properties of radicals, the square root of -4, I can separate that into two separate factors of 4 and -1. And by doing that, what I've done is I've separated the square root number part from the negative part of the square root. And so when I do that, the -1, then that's where I get my imaginary number I. And when I do the square root of 4, that's where I get my 2, right? The square root of 4 is 2. Okay, so let's look at these two examples I have down here. So if I do the square root of -25, the first thing I want to do is separate that into the real number part, which would be the square root of 25, and the imaginary number part, which is the -1. 25 times -1 is still -25. Okay, well I can square root the 25 and just get 5, and I can square root the -1 and, whoops, sorry about that, -1, the square root of -1 is always going to be I. Okay, so I can do the square root of -8 in a similar fashion. Now, if you remember, we would separate the real number part from the imaginary number part, right? Square root of 8 times the square root of -1. And if I simplify my square root of -8, that simplifies as 2 square root 2. Okay. And then my square root of -1 makes I. Now, just for convention's sake and for the sake of saving some confusion when you're writing these, what we will typically do is that I will go in the middle with the 2 between your square root and your coefficient. And I always say that part of that is because if you write anything after your square root sign, it can often be mistaken or hard to determine whether that belongs under the radical sign and you just didn't make your line long enough on top, or something like this. And so that sort of eliminates that confusion as far as what actually belongs under the square root and what doesn't. So we'll move the I over there in front of the radical sign with the 2 and keep it there. So that's sort of like the standard format for writing those. Okay, so a complex number, if we move on, is then a number that can be written in the form A plus BI, where A is what we would call the real number part, and the BI is your imaginary number part. Okay, so you put a real number part and an imaginary number part, and you get something that we call a complex number. So down here at the bottom of the screen, I just have some different examples of what complex numbers would look like. You have 4 plus 3i, and negative 3 plus 9i, and 7 minus I. These are all complex numbers where you have a real number. Okay, those are my real numbers. And then I have the imaginary number part. Okay, making it what we call a complex number because it has both a real part and an imaginary part to it. Okay, so the second objective that we had for this lesson was to be able to add and subtract and even multiply these complex numbers. So what I want to do first is the addition and subtraction, and I think you'll find this fairly simple because for the most part we're going to treat that imaginary number just like we would a variable. Okay, so like in this case we're going to combine like terms. A real number is only a like term with a real number. And an imaginary number can only be a like term with an imaginary number. So really, simplifying these is not any different than simplifying if I would have put an x or a y or something like that in here. I just simply combine my like terms. So since this is an addition problem, sorry, I keep doing that. Since this is an addition problem, I'm going to simply combine whatever I have as like terms. And with addition here, I could actually just remove my parentheses without changing anything about my problem. So negative 2 plus 6i, no signs change. And then just simply combine together my like terms. Like 5 and negative 2, those are both the real numbers. So 5 and negative 2 make 3. And then I combine the 7i and the 6i, which are both positive, and I get a 13i. And since I have a real number and an imaginary number, I can't combine those together. Those are not like terms, so my answer is just going to remain as 3 plus 13i. Now, the second thing I'm going to do here is a subtraction problem. Now, the one thing about these is that you have to be a little more careful with your sign because the subtraction sign applies to both the real and the imaginary part of your complex number. So if I want to remove my parentheses, it's going to look like this. 8 plus 3i minus 2 minus 4i. So I have to get that I, or that minus, sorry, to both the real and the imaginary part. Okay, and then I combine my like terms like the last problem. So 8 and a negative 2 make a positive 6, and a 3i minus a 4i gives me a negative 1i, or just minus I. So my final answer there is 6 minus I. Okay, so adding and subtracting, fairly simple. Treat like terms like normal and combine them until you can't combine any more like terms. Now multiplying, same situation. We're going to treat the I, the imaginary number, as if it was a variable until I finish multiplying. Because there's one thing that I do know about I. If I is equal to the square root of negative 1, I squared, okay, let's think about that, is the square root of negative 1 squared. What am I going to get if I square the square root of negative 1? Okay, well that's actually going to be negative 1. So there is a way for the imaginary number to actually become a real number again, and that is whenever you have I squared is actually going to become negative 1. Okay, those are equivalent. All right, so let's look at how we would do this. Okay, if I was using this as if it was just a variable, and I was multiplying 5i times negative 4i, I just simply would multiply those two things together and get negative 20i squared. Now, if I was really a variable, that would be my answer. But since I is actually an imaginary number, and I know that I squared is equal to negative 1, I can actually take the I squared and replace it with negative 1, right? Substitution. And negative 20 times negative 1 will give me a final answer of 20. So what I actually did is I took two imaginary numbers, multiplied them together, and got a real number as my answer, 20. Okay, what do you think about this one? 6i times 3i minus 2i, or 3 minus 2i. This problem looks like a problem where I would use my distributive property. So we'll do that. 6i times 3 makes 18i, minus 6i times 2i is going to be 12i squared. Okay, so we have some substituting to do. 18i will just be 18i, and the I squared is going to be replaced with -1, which is going to give me 18i plus 12. Now, a typical complex number is written with the real number first, so I'll put my 12 first, and then I'll put my imaginary number second, just to get it into its normal format there. 12 plus 18i. Okay, now the second part we're going to do here is we're actually going to take the 4 minus 9i times the 4 plus 3i. And again, what am I going to do to get these multiplied together? I'm going to use my distributive property, or FOIL, as you would call it, so that I can multiply everything together. So let's see, we'll have 4 times 4, that's 16. And we'll have 4 times 3i, which is 12i. We'll have -9 times 4, which is -36i. And then we'll have -9i plus times +3i, which is going to be -27i squared. Okay, so we have a little bit of simplifying to do on this one. One thing I see that I can do is combine my like terms in the middle. The other thing I can do is take care of this I squared here. So I'm going to get 16. Positive 12i, -36i is going to make me -24i. And -27 times -1, which gives me 16 minus 24i plus 27. So essentially, got one more like term to combine together, 16 and 27. So I'm going to end up with 43 minus 24i. And that's in the standard form for a complex number. Okay, so now sometimes when I solve equations, like last time we solved equations by using the square root, and so sometimes we have complex solutions from solving those equations. Okay, let me give you a couple of examples, or at least one here. So if I have 4x squared plus 100 equals 0, this is a problem that I could solve by using square roots, right? It doesn't have a bx term in it. So to do that, what I'm going to do is I'm actually going to start by subtracting my 100 from both sides. And you can see here where that complex solution is going to come in, because I end up with this. 4x squared equals -100. And when I divide by 4, I end up with x squared equals -25. I square root both sides, and I get x is equal to plus or minus the square root of -25. Now, when I want to do something with the square root of -25, I have two things to worry about here. First of all, I do have to do the plus and minus because I am solving an equation and I don't really know if it's the positive or the negative, but I need to do the square root of -25. Okay, so I'm going to end up with a square root of -25, which is 5i, right? 5 for the 25, I for the negative. And then I'm going to end up, because it's an equation, I'm going to end up with both positive 5i and -5i. So that's actually going to have two imaginary solutions. Okay, not even technically complex because there's no number there in front, no real number part. Okay, so this one would be the same way. I would end up doing 3x squared, subtract my 48, so that equals -48. Divide both sides by 3. I get x squared equals -16. I go to square root both sides, and I end up with x equals plus or minus the square root of -16, which is x equals plus or minus 4i, which I would write out as 4i and -4i. Okay, so again, actually imaginary solutions for those two problems.